In this video, we will discuss about three fundamental laws of thermodynamics, such as the first law, second law, and the zeroth law. So we'll start with the first law. It is the most fundamental law of universe, which states that the total energy of our universe can neither increase or decrease. That is, it remains conserved. However, there will be continuous exchange of energy from one form to the other. Let us understand this with an example. A piece of stone, suppose, is kept at the peak of a hill. Now at this point, its kinetic energy is zero and the potential energy is maximum. Now, if the stone starts falling, then due to the pull of gravity, it will start gaining kinetic energy. Now, where from this kinetic energy is coming? It is actually the transformation of potential energy into the kinetic energy. The total energy, however, is still the same. Now, as the stone comes near the ground, the kinetic energy becomes maximum and potential energy is almost zero near the ground because height is very less. So this is how the same energy keeps changing forms. Next, if we pass electricity through a conductor, it gets heated. This heat is not something that is getting created. In fact, the heat is obtained. The heat that is obtained is the result of conversion of electricity into thermal energy. This happens because as the electrons flows through the conductor, the conductor resists this flow, and this resistance gives rise to heat. Finally, just one more example I'll give. When we burn any fuel, we get heat out of it. This heat is again the result of conversion of chemical energy present in the fuel into thermal energy. Okay. Next comes the second law. We know that for a process to occur naturally, the first law has to be satisfied. But only by satisfying the first law does not guarantee the occurrence of a process. Let us understand this with an example. Suppose if I pass electricity through a wire, it gets heated according to the first law. But is the reverse case possible in nature? That is, if I heat the wire, will I get electricity? Definitely no. Similarly, heat will flow from a hot body to cold body naturally, but the reverse case is impossible. One more example. Water will always flow from the overhead tank to the second tank that is kept below. It is quite natural. But the reverse flow from the downward tank to the overhead tank is not possible naturally. We need some kind of machines to do this. It is because processes in nature have a definite direction of occurrence. And this is exactly why we need the second law. That is, it tells us about the direction of occurrence of a process. One more utility of the second law is that it tells us about the quality of energy. See, the first law is concerned only with the quantity of energy and transformation of this quantity from one form to the other. But the second law is concerned with both the quantity as well as the quality. Okay, for example, heat and work are both different forms of energy. However, they differ largely from one another based on the quality. Work is generally considered as a high-grade energy, and any kind of work done results in heat without any effort. But conversion of heat to work is not always possible naturally. We need specialized engines for this. Let me explain again. Suppose I have a pedal wheel. Now, if I rotate it very fast, some amount of heat will be generated in the water due to the disturbance. This is a case of conversion of work into heat. But in the reverse case, if I supply heat in the water, the pedal wheel will never start to rotate. That is, heat to work conversion is not possible. Okay, naturally. Now, the second law of thermodynamics can be expressed in two different important statements. The first one is the Clausius statement, and the second one is Kelvin-Planck statement. So let us see what is this. According to the Clausius statement, it is impossible for a device to extract heat from a cold body and deliver it to a hot body naturally. That is, in a natural process, heat always flows from a hot body to a colder body. The reverse case is not possible. However, to extract heat from a cold body and deliver it to a body at a high temperature, we need to do some work. The refrigerator is a classic example of this. It takes electricity and extracts heat from a low temperature sink and releases this heat to a high temperature surrounding. The second statement, that is the Kelvin-Planck statement, says that no heat engine can convert 100% of the heat received into work. That is, it has to reject some amount of heat into a low temperature reservoir, that is the sink. The second law also introduces a very important concept called entropy. I will explain this concept in the subsequent videos in details. In simplest terms, entropy is the degree of randomness of a system. So the second law says that entropy of a universe is always increasing, and in order to reduce the entropy of a system, we need to do some work, which in turn again increases the entropy of the surrounding. Okay, so this was all about the second law. Now, finally, the zeroth law. This law came actually at a very much later stage, much later than the introduction of the remaining two laws. Since it is a very important law which gives us an idea about temperature, so it has been decided to keep it before the first law as well as second law. Hence, we call it the zeroth law instead of the third law. Now, the zeroth law of thermodynamics states that if two bodies A and B are separately in thermal equilibrium with a third body C, then these two bodies A and B will be in equilibrium with each other, even though they are not in direct contact with each other. Okay, let us understand this with an example. Suppose A and B are separated by an insulator, say wood. In this case, there will be no heat exchange between A and B. Now, if a third body C is introduced and it is in contact with A and B by a conducting material, say copper, then heat will start flowing from C to A and B, since C is at a higher temperature. The heat transfer will continue to take place till C is in the same temperature as A and B. So we see that all these three bodies are now in the same temperature. So A and B, although have no contact, will still come in the same will still come in equilibrium. Please note that apart from these three laws, there is one more important law of thermodynamics, that is the third law, which I have not explained here in this video. In subsequent lectures, I will explain it. Okay, so this was all about the three laws of thermodynamics. For more such informative videos, please subscribe MagVidya. Thank you.